let's get started. Let's talk about the Bernoulli processes, which is the first simplest random process that we're going to study in this course. Okay, so Bernoulli process is that at each minute or time slot or unit time, minute can be a second or minute can be 1 hour. So minute is just a nominal unit time. So at each minute, we toss a coin that has a probability of head P. And we're going to repeatedly do these things over an infinite time horizon. That's the Bernoulli process. And then the examples of the Bernoulli processes is the sequence of the lottery wins and loses over time. So win or lose is just a success or failure. And we're going to look at the sequence of those things. What about the customers to a bank? And if we just look at a very small time interval, then we can assume that the maximum number of customers to a bank over that time interval is just 1. So it's a 0 and 1. No customer or customer. What about the clicks to a server? So for example, when you run a server, web server, then you are receiving the clicks from other people. And similarly, when we just look at a very small time interval, then the maximum number of clicks is just 1. So the presence of the clicks or the absence of the clicks, 0 and 1. Those are the Bernoulli random process. So formally, Bernoulli random process is a sequence of independent Bernoulli trials, like x1 and x2 and x3. Here the important setting is an independent. So what we do in the x1 and what we do x2, they are independent. Obviously x3, x4, and x5, those are all independent. Okay, that's why we say that the Bernoulli process is one of the simplest process, but it's good to start from a very simple process and then we're going to extend to a more complex process. We call index 1, 2, 3, 4 the time slots, or simply slots, or sometimes we just use the unit time. So again, as I mentioned before, it can be 1 hour, 1 minute, 1 second, but the important assumption is the Bernoulli trial. So a random outcome is nothing but an infinite sequence of the 0 and 1. Like 001, 00011, or 11000011, and so on. So we have various kinds of the random outcomes. If we collect all of them, then that constitutes an omega. Discrete time and discrete value, where the discrete value is like what? The value is 0 or 1, so that's a discrete value. As I mentioned before, that's one of the simplest random process. And also we can regard this Bernoulli process as a type of arrival process. When you think about this example, like customers to a bank or the clicks to a server, those kinds of things are basically our arrivals, right? But here we only look at the existence of arrival or no arrival, like 0 and 1. Okay, so you may think that this Bernoulli random process is too simple, so we don't use this random process in a practice. But the answer is no, because as I mentioned before, if we think about a very small time interval, small time slot, then the assumption of just the 0 and 1 is not very restricted. But still, the Bernoulli process is very simple that allow us to mathematically analyze what happens in the Bernoulli process. So mathematical tractability as well as the practicability, those two features are sometimes possible in these Bernoulli processes. We're going to talk about the important questions about the Bernoulli processes. But rather than giving you a list of the questions from my explanation, why don't you pause the video and think about the important questions that you can ask about the random processes. So listing up those questions will give you the chance to think about what are the important things and what are the unimportant things. So please pause the video and take some time to write down as many questions as possible that you are wondering about this Bernoulli process. Okay, so how many questions did you write down? So again, as many questions as possible would be good. Let me give you my questions. So first question that I'm wondering is that what is the number of arrivals in the first n slot? So I believe that that is a very basic question. So we just see the infinite sequence of the 0 and 1, and I just look at a finite window, which is an n slot, first n slot, and just know the what is the number of arrivals, what is the number of successes. And obviously this is a random variable, so it has to have some distributions and as a summary like expectation and the variance. If we let the Sn to be the x1 plus x2 up to the xn, the number of arrivals in the first n questions is the value of Sn, right? Because like 0, 1, 0, 0, 0, 1, 1. So if we look at the value of the S1, that corresponds to the number of arrivals. And we know that this Sn is a binomial random variable with parameter n and p. Because it's a collection of the Bernoulli trials, independent Bernoulli trials. So Sn is follows the binomial with the parameter np, and we know the expectation and the variance. So that's an easy question. Oh, by the way, so this will hold for any n consecutive slot, not just the first n slots, but like the slot from the I to the I plus n minus 1. These are the n slots, right? Why is that? Because what happens in the time I and what happens in the time j, they are independent. Whatever we pick just the n consecutive slots out of any time window, then the number of arrivals over these n slots are equal, not just first n slots, right? Because of the independence across the slots, right? The second question is the number of slots until we see the first arrival. So when we start this Bernoulli process, then sometimes we like no arrival, and the arrival. Then in that case, the number of slots until the first arrival is 3. Okay? Like no arrival, and the arrival, then this is 6. So we're going to denote the T1 as the number of slots until we see the first arrival. Obviously, the T1 is a random variable, and we are wondering about what is this T1 random variable and the distribution and the expectation and so on. Now you think about this question, then I think that the T1 is the random variable you know pretty well. So what is that random variable? Yeah, true. That is the geometric random variable with the parameter p. Because the geometric random variable is the number of trials until we first see the success. So that's exactly talking about this. And we know what the geometric random variable, and if you go back to, if you don't remember what is the geometric random variable, please go to the lecture 3, then you see the section that kind of discrete famous random variables that where we discussed this geometric random variable, and the expectation was the 1 minus p and the variance was 1 minus p over p squared. This was the PMF of the geometric random variable. Okay. Oh, geometric random variable. Then immediately that reminds us the memoryless property. So what is the memoryless property again? So try to remember what it means, and also definition. Condition on no first arrival until at some time. Like for example, up to the third time slots, there was no first arrival. The question is how many more slots that I need to wait until I first see the first arrival. That does not depend on the first 3 slots that I have waited. I just see the same geometric random variable irrespective of the number of slots of no first arrival. So that was the memoryless property. As you remember, the geometric is the only random variable that has the memoryless property, and in the continuous random variable, exponential random variable was the memoryless random variable. Okay, but more than that, using this kind of memoryless property and the independence across time slots, they will lead us many useful properties, and also that allows us to solve the many kind of hard problems very quickly if we use the property of this memoryless and the independence across time slots. We're going to look at various examples of why this is true.